Hello everyone. Today we are going to read a very important article which has been come up in online mode but in a hard copy may be published in December 15 issue 2021 in IEEE Photonics Technology Letters, which is very important journal in the field of photonics, optical communication, etc. So the title of our article is net 300 gigabit per second per wavelength per lambda transmission over 2 kilometer of single mode fiber with a silicon photonics Mach Zehnder modulator. So here data rate has been given, that is the 300 Gbps per wavelength, means on only single wavelength. Suppose wavelength is at 1550 nanometer, with that only the data rate is 300, and this transmission has been carried over 2 kilometer on single mode fiber with the Mach-Zehnder interferometer. So most of the time what we have seen that Mach-Zehnder interferometer based optical monitor was used in the data center where communication path length was very small. Now here it has been used for long haul communication system. So coming to the list of authors, Muhammad Samuel Alam, graduate students member IEEE, then Yuan Lang Lee, graduate student again from IEEE, then Maxim Jacques Isam Barika, again a graduate student, then Ping Chiang Ko and David V. Plant, fellow IEEE. So these are, I think, not well known to be these researchers. Anyway, let us see what is the contribution of these researchers. So abstract implying our 47 gigabit per uh, gig, uh, 47 gigahertz bandwidth silicon photonics traveling wave Mach-Zehnder modulator, that is TWMZM. We demonstrate the transmission of 134 gigabaud PAM4, that is the modulation format PAM4, net 250 Gbps at a bit error rate below the 6.7% overhead hard decision forward error correction hard decision forward error correction, that is HDFAC, threshold of 3.8 into 10 to power minus 3 over 2 kilometer of standard single mode fiber in the O band with only linear feed forward equalizers FEE with the aid of nonlinear pre-distortion and FFE, that is the feed forward equalizers. We transmit 115 gigabaud PAM8 net 288 Gbps and 305 Gbps PS PAM8 above the 19.02% overhead soft decision FEC, that is the forward error connection, with a normalized general mutual information threshold of 0.8798. These results are the highest reported net rates for an all silicon modulator in an intensity modulation direct reduction scheme. Okay, that is also very important. Intensity modulation direct reduction scheme. This is, it means this is not a coherent modulation scheme. Okay, so this is the abstract. So in abstract, it's very prominent things are given, and some of the not as such modulator design, but here as a system design. So the bandwidth of this modulator is 47. This is very important thing which we have to keep into mind, that what is the bandwidth? Bandwidth of MZM is 47 gigahertz. And the modulation formats which has been used here, that is the PAM. So PAM modulation formats, PAM4, PAM8, okay. And some feed forward error correction technique, including equalizers, and the data rate, and this has been used for single mode fiber O band. O band is just below to C band. That is the C band, suppose 1525 to 1565 nanometer. This is the C band. Just below to that O band, O is original band, C is the conventional band. So let us, we will see what is the exact wavelength range for which this communication system has been established. And data rate, as you can see, 250 Gbps for PAM4, and then 288 Gbps as well as 305 Gbps. So that is why in title you can see average 300 is given. Now let us move. What is the introduction? And keywords, data center interconnects. As I was telling that most of the time, this silicon modulator has been used for data center. Silicon photonics, pulse amplitude modulation. Now this is the full form of PAM. So PAM 4, PAM 8. So these are the order of PAM modulation scheme. So to keep with the growing demand for high bandwidth application, the data traffic inside data center is increasing and intensity modulation direct detection systems are preferred in this short reach scenario, that is the 500 meter to 10 kilometer, due to their cost and power efficiency. So you can see it begins uh, the need of this communication system. Why we are going for towards the optical communication system? The very reason is that there is a growing demand for high bandwidth application, particularly data center data traffic, and and more specifically for intensity modulation direct detection scheme, which is the incoherent modulation scheme. And this incoherent modulation scheme has, of course, inferior performance over to coherent communication, but because of their cost as well as power efficiency in short range communication, it has still relevancy. That is why it has been used here, intensity modulation direct detection. However, if the same modulation scheme can be, you can use this what is called coherent modulation, so there may be possibilities of increasing the data rate further. So from here, this paper itself is giving a scope of doing some more work. Now, coming to next line, among different intensity modulation direct detection scheme, intensity modulation means amplitude is modulated, amplitude of the laser is modulated as per the modulating signal, and then your direct detection scheme is for photodetector is directly converting your light signal into electrical signal, equivalent electrical signal. So among different IMDD scheme, pulse amplitude modulation, that is PAM, is a suitable choice for its low complexity and 4-lane 400 gigabit Ethernet with PAM4 has already been standardized for this region. So why they have selected PAM4? The where in each line we have to see that whenever they are using any scheme, they are justifying also. Like here, among different intensity modulation direct detection scheme, PAM modulation scheme is suitable. Why? Because of its low complexity and 4-lane 400 GB Ethernet with PAM4 has, and why? Because it has been standardized. This PAM4 modulation scheme has been standardized by standardization organization. Now next, the 800G multi-source agreement MSA is now working to extend this capacity to 800 GBE, and recently has released the first 200 GB per lane PAM4 industry specification. So this is also, we have to see towards this 800G, the multi-source agreement also there. Now compared with 100G per lane, 200G per lane can provide better cost optimization and is thus expected to become the foundation for future 800G GBE and 1.6 TBE short reach interconnect standard. So we have to see this what is the context. The work which is being reported here is very much relevance in the path of growing technology. That is to say, 800G per line. Then people are moving towards 800 GB. So 400 GB is already standardized, and now people are moving towards 800G. In addition, 250 Gbps per wavelength solution will be an attractive choice for intra data center interconnects, DCIs, and metro hall applications requiring 1 TBE data communication. So they are now trying to justify why they are concentrating on this 300 net. So within 300 net, 250, 288, and 300. So this line goes uh, in line of that. So to go beyond 200 Gbps per wavelength, high operational bandwidth of each transceiver component is essential. The limited electro-optic bandwidth of the modulator is a major challenge in achieving this objective. The limiting electro-optic bandwidth, okay, without restoring to complex digital signal processing and advanced modulation formats like subcarrier multiplexing or discrete multi-tone DMT signaling. High bandwidth directly modulated lasers DML, electro-absorption modulator with distributed feedback lasers, plasmonic modulators, or a thin film lithium niobate modulators have therefore been used in recent 200 Gbps per lambda IMDD experiments. But none of these modulators can be entirely fabricated at a commercial scale. On the other hand, silicon photonics offers lower cost and excellent production yield with co-packaging capability and plays a prominent role in the DCI industry. Depletion mode traveling wave series push-pull silicon Alexander interferometer modulator have shown the potential for high EO bandwidth up to 60 GHz and can therefore be regarded as a suitable choice for the next generation high-speed transceiver. So we have previously reported the transmission of net 200 Gbps with a segmented electrode Alexander modulator with recently shown that 220 Gbps transmission with a single segment silicon photonics Alexander modulator over 2 km of single mode fiber in the O band. 4 channel 800 Gbps, that is 200 Gbps per channel. They have they might have used WDM gross bit transmission with PAM4 over 1 km of single mode fiber in the C band is also demonstrated. A silicon microlink modulator MRM with 3 dB bandwidth greater than 64 gigahertz has been recently employed in a 100 gigabaud PAM4 demonstration at back-to-back. But not 200 Gbps with PAM4 signaling, an important milestone for DCI marker, has not yet been demonstrated with an all silicon modulator. In figure 1, we summarize the recent records for high speed intensity modulation direct direction transmission with silicon photonic modulator. So in our current work, a lead we with only a linear feed forward equalizers and a simple 3-volt peak to peak driving signal on a conventional silicon photonic modulator. We transmit 134 GB gigabaud PAM4 net 250 Gbps below the 6.7 overhead HDFEC BER threshold of 3.8 into 10 to the power minus 3 and 115 gigabaud PAM8 net 288 gigabit above the 19.02 OH HDFEC and GMI threshold of 0.87898 over 2 km of single mode fiber in the O band. With the aid of post filter and maximum likelihood sequence detection, we extend this transmission capacity to 140 Gbps. for PAM4 signaling. These results are achieved with our silicon photonics SPP traveling wave modulator with 2.5 mm phase shifter length and a 256 GSAS uh, silicon germanium AWG. To explore the capacity limit with our silicon photonic Alexander modulator, we adopt probabilistic shaping and show net 310 Gbps operation. We also successfully transmit net 280 Gbps PAM8 and net 234 Gbps PAM4 signal with a single AWG channel operation at 128 GB G, S per signal. To the best of our knowledge, these are the highest reported net rates with the silicon photonics modulator in an IMDD system. We also explore different DSP techniques to deal with inter-symbol interference and system nonlinearity and compare their performance among different PAM formats. So let us see what is the figure 1. It is here. We can see figure 1 review of recent high-speed silicon photonics intensity modulation direct detection things. So here symbol rate 75, 85, 95, 105, 115, 125, 135 and net bit rate per lambda. So it starts from 150, then 175, 200, 225, 250, 275, 300 and we can see here about this band with rate symbol rate O band lies this this is the O band and this is silicon photonics measured modulator O band micro regenerator regenerator and this is blue color PAM 4 red color PAM 8 and green color this work they are using PS PAM 8 as well as PM8. So this work over. So now scope is coming to go for C band. C band same work we can go for the C band as well as for L band. So anyone is there to so we will move next to experimental setup, but we will have a break. We are meeting soon.